Thank you. Hi, good morning, everyone. My name is Yi-Hai Fang. I'm from Monash University in Melbourne, Australia. So it's my first time in New Zealand, and this is the picture I took from the apartment I'm staying. So despite the spectacular view here, what I was interested about is the number of cranes in this picture, because that's related to the topic I'm going to present today. So based on my count, there are 17 cranes. There are the luffing boom tower cranes, the port cranes, and in the far end, the other side of the harbor, you have another 2 tower cranes. So, I mean, the number of the cranes kind of indicates the prosperous economy and the booming construction industry, and also reflects the increasing number of construction projects happening in the major cities. So you can see how the crane operator would face the challenge in terms of maneuver the crane and the load in proximity to the surrounding buildings in a confined space. So this study is about another scenario, but it's similar. It's about the blind lift scenario on offshore platforms. And I'm going to introduce how we attempt to improve the safety in blind lift through real-time sensing and visualization. So if I've been to an offshore platform, you'll understand how congested the site layout is on these platforms. They want to fully utilize every inch of space on platform. So you can expect the layout is very congested. And there are a lot of blind lift happening on the platform in terms of transporting the supplies, materials, and sometimes even personnel from the vessels. And in those cases, the operator has to rely on the signal person, the video communication, and that's not 100% error-proof. So what we're looking at here is to find or to develop a system that will help the operator to understand the potential safety risks associated with the operation, and to provide basically a safety net in case the operator misses any risks or make a wrong decision. So we're actually not short of lift assistance systems. For example, on the top left corner, there's a crane camera system, which provide the operator a bird view to the load being lifted. And the limitation of that is it gives you a unobstructed view, but it doesn't give you the depth perception, the height of the load from the ground level, or the monitoring of clearance to surrounding objects. And there are also other research in terms of using real-time location systems, RFID or ultra-wideband, try to track the location of the tags mounted on the crane parts. So we can get the absolute location of these crane parts in real time. And also there are other attempts in using LiDAR or vision-based methods to track the pose of crane and other heavy equipment and visualize the motion of the pose in real time. But they're subject to some limitations in terms of the occlusion of the site and also the system setup. It requires a permanent or a reliable setup of the LiDAR or camera system. So here our objective is to find a accurate and robust way to sense the crane motion in real time and also visualize it to the operator in real time. So the first task we're trying to accomplish here is to capture the crane motion in real time. So the angle of the boom, the slew angle of the entire superstructure. And this work was inspired by some early work from Dr. Gang Li from Yangtze University. And here we're using rotary encoders and digital inclinometers to capture these critical motions in order to reconstruct the entire crane motion in real time. And the second part, which is very important, especially in the offshore platform, is to monitor the load sway, because the operator has in many cases, a very narrow corridor to maneuver the load. So it's very important to monitor load sway, either as a result of excessive maneuver or because of strong wind. And here we propose two methods. One is using inertial measurement unit, try to capture the orientation of the load, and then transform that to the absolute location of the load. And another method is using computer vision with a camera image captured by a top view camera, and try to track the location of the load in the image frame. So I'll explain why we use two different methods and in which scenario they're more suitable. So eventually, when we have the crane motion and load sway motion, we need to integrate them, fuse the data, and visualize it to the operator in order to assist the decision making and operation. So eventually, the visualization and user interface is designed to assist the operator in real time. And at the same time, we want to minimize the disruption to the operator's routine work. So I'll explain later how we integrate the voice control to free the operator's hands with the user interface. So this is how we set up and deploy the sensor system. So we use the rotary encoders to measure the boom slew angle and the hoist cable length. And we used a digital inclinometer to measure the boom lift angle. And all these sensors are wirely connected to a central unit to collect this data. And then for the MU sensor, we mounted on the hook block, and that is wirely connected to the receiver of the IMU sensor. So in this particular experiment, we used IMU method and explain how that worked out. In terms of the visualization and user interface, we used a 11-inch screen and visualized the real-time crane motion in the crane cab to the operator. Here you can see the background is constructed beforehand. So it's based on the point cloud laser scan of the platform. So this user interface will allow the operator to change the perspectives in order to avoid any blind spot, and also monitors the clearance between the load and other crane parts to the surrounding objects. So it can provide warnings to the operator in case of any violation of the safety threshold. So we did a case study with our industry partner on one of the biggest offshore platforms. This platform has two cranes on board, and we actually went there and did a laser scan and built this point cloud data of the platform. And then we manually built this 3D model in order to reflect the platform structures in the user interface or in the virtual environment. So this is just a quick demo of how the system worked. On the bottom part is the user interface. It shows a bird view, which can be controlled by the voice command from the operator. And then it shows a side view and a top view. Basically give the operator more information about the vertical and horizontal clearance. And the red part actually is the rig. So it's movable. It can change its location along a rail. So we include that part in this program so it can reflect the actual location of the rig. So just a quick video showing the voice control. It's still early prototype, so there's a little bit delay between the command and the action in the program.
Zoom out. Right.
So we didn't develop the algorithm from scratch. It's a commercial available product. So what we did is integration with the Unity game engine to realize this function. And of course, we're interested about the accuracy of this system in terms of tracking the hook or the load position. So we did some preliminary tests. We choose 4 blind lift locations on the platform. And then we try to find the positioning arrow of the system. And the end result is actually not to our satisfaction. It has a horizontal arrow, average arrow of 0.9 meters and 0.7 in the vertical positioning. This arrow is partially due to the sensor setup. I mean, it's not, it's a temporary setup for the sensors. So eventually, if we can work with the crane vendor or manufacturer, we can integrate the sensor with the crane system itself. So that arrow can be minimized. But actually, the major contributor here to these arrows is because of the IMU sensor we used. Because you know the gyroscope on the IMU is very sensitive to magnetic interference. And this whole platform is a big piece of metal. So that actually created a big problem for us. So actually, when we come back from the experiment, we want to investigate another method, particularly in the offshore platform scenario. So we explored a computer vision method. So basically use the load camera, the crane camera, to capture the load from top view. And then we firstly convert the color space from RGB to LAB. And then it involves some manual process in terms of specifying the foreground color for the load. And then we use a expand and contract scheme to track the load position across image frames, and then construct a bounding box to reflect the load position in the image frame. And then with the known length of the cable and then the focal length of the camera, we can calculate the relative location of this load to the camera location. And we want to understand how this method performs in the lab test and the field test. So firstly, we did a indoor lab test. And we basically made 2 scenarios. One is with a very simple background. Another one is a more complex background. And we want to understand how the method performed in different complexity of the background, which is a big factor in the offshore platform or any crane lift operations. And we also set different cable length, because that also affects the accuracy of the vision tracking. We also use the footage from an earlier experiment out in the field, trying to see how the algorithm performs in real time, in a real life setting. And the red square shows you the track load position as a result of the algorithm, and the yellow one shows the ground truth. And eventually, we had 8 scenarios in indoor and outdoor test with different cable length. And that shows us how the algorithm performs in different settings. And the mean position arrow is from 0.2 centimeters to 15 centimeters. And we also are interested in the rotation arrow, because if we want to very accurately track the load position. We also want to know the rotation orientation of the load, especially when it's a rebar or it's a linear load. So we found that the tracking accuracy is sensitive to the background complexity and cable length, and that's definitely something we want to improve in our future work. So one possible solution is to attach a visually significant marker onto the load, and that's something we want to try next. So in conclusion, we proposed a system, use real-time sensing and visualization, and the purpose is to increase the safety and operators' confidence in blind lift. And we also see a big benefit of this type of system in remote controlling scenarios, which actually we see a lot of small cranes in residential buildings. They're using a remote control crane where the operator is on the ground. And in our next step, as I said, we want to improve the accuracy and robustness of the computer vision-based method to track the crane load. And we're going to have another, the second phase of the experiment on the offshore platform, where we want to test out how it works in real life. And also, currently, it's the computer vision part is offline; it's not processed in real time. So that's another work we want to do in the future. And we also want to understand how the operator and the lift crew actually perceives this system. So the usability and effectiveness in terms of improving the lift safety and productivity performance is also very interesting to us. So with this, that concludes my presentation. Thank you very much.